Okay, can you all hear me? Yeah, works? Okay, so yeah, so I will give 3 lectures on categorical traces, and that's kind of a topic that has gotten a lot of attention, say, over the last 5 to 10 years. And it's the one that's used critically in the construction of Xinwenzhou and of Benzi, Shen, Helm-Nadler. And so, but what I'm going to talk about, like in the 3 lectures, is like more the abstract framework for it. And I think kind of both David and Xinwen will use this in more like in a more precise situation to explain their work. Okay, and also a disclaimer. So kind of these lectures have basically started in a bar 2 years ago with David, and so kind of a continuation of this. Okay, so oops. Okay, so I'm left-handed, and the arrow to point back is on the left, so I might click on this a few times during the talk. Sorry about this. Okay, so the general idea for traces, okay, classically what you take V of finite dimensional vector spaces over K, F, an endomorphism, and you define the trace of F on V, and I think the scalar. And so the general idea that's kind of behind this and will serve as kind of some kind of organizational principle for the 3 lectures is that the trace kind of takes an object in some kind of category and like extracts something that's lower category, like at the lower categorical level. Oops, sorry. Okay, so kind of the point is that you have like objects in categories. So like vector spaces, representations, and so on. And the trace, so that's kind of a 0 category itself. And the trace is a scalar. Okay, I think it's doing the same as for Paul. It's erasing when I want, sorry. So like scalars, functions, and so on, or characters. No, not functors yet. Functions and so on. So this is kind of what I want to call a -1 category. Okay, and the trace is something that kind of goes from 0 to -1. And today, we're going to go from categories, so which is a 1 category, implicitly infini 1, down to objects in categories. And kind of the first instance of what you want to call a categorical trace is like this procedure of going from a category to an object. But the formalism is rather robust and rather abstract as well. But so it doesn't prevent you from going from, say, 2 categories down to, so this time 1 categories. And okay, some people have already asked me, like, what happens if I want to do 3 or 4 categories? And you can just keep going if you want. What you need is a formalism that's like robust enough for this to make sense, which presumably we now have. But okay, I will stop here for the lectures, kind of. So, and oops, shit. And so this is today, and this will be tomorrow. And on Friday, I will basically discuss the composition of these first 2 maps. Okay. All right, so let's start with some definitions. So I will first fix O, and it will be some ambient symmetric monoidal category. And okay, so very quickly, it's going to be an infinite category. For now, it can be anything. So definition 1. So X is in O is dualizable. And okay, I'm saying dualizable and not left or right because the ambient thing is symmetric. So if there exists an object X dual and a pair of morphisms, X tensor X dual to 1, so the monoidal unit in the category evaluation, and 1 to X dual tensor X, such that the compositions, so X to X dual to X, back down to X, and here you do identity, so this is co-evaluation, tensor co-ev, and F tensor identity is the identity and the same for x dual. Okay, so this is coev. Sorry. So which one do we want here? Sorry?
No, sorry.
Yeah, coev tensor identity. Yeah. And f tensor identity. Yeah. Okay. Has to be the identity as well. Okay. So, all right. And so kind of the example is that if you take O to be the category of vector spaces, the dualizable objects are exactly the finite dimensional object, the finite dimensional K vector spaces.
Sorry, should be identical tensor.
Where?
The last horizontal small arrow.
Oh, yeah, thank you. So identity tensor F. Yeah, thank you. Okay, and then so second definition. So if I take X, O, in O some dualizable object, and F some endomorphism, I can define the trace of F on X as an object. It is going to be an element or an object in the endofunctors of 1, in the endomorphism of 1 in O, and it's going to be the following composition. So you go via coevaluation to X tensor X dual, you F tensor identity, and then you evaluate down to 1. And so the exercise is if you take O to be the category of vector spaces, then this notion of trace is the usual notion of trace. Of trace in, so the unit is K, the one-dimensional vector space, and it's again K. Okay, so exercise, just compute this thing when you have a finite dimensional vector space and just find multiplication by the trace as a scalar. Okay. All right. Sorry, so this thing keeps sliding down. So if you can't hear me at some point, just yell at me. Like this? Okay, let's try it. All right, and so the main situation for today is we'll take O to be so the category of presentable K-linear categories. So of presentable, stable, K-linear categories. All right, and the monoidal structure is given by Lurie's tensor product. So okay, and so rather than defining it precisely, and in general, so I mean, so if you take A and B, two such objects, you can define A tensor B, and it's again an object here. So I will shorten this by just PR. And so as an object is defined via the obvious universal properties that you care about, namely, so kind of a bilinear functor out of this, which is continuous in both variables, factors uniquely through this tensor product as a functor out of the tensor product. So it's really just the same universal property you would do for modules. And the thing is that doesn't quite tells you what the resulting category is. And it's kind of the same problem that you would have when you tensor modules over rings. Okay, you can define the thing, kind of, but naively, you not necessarily have a general description for it. And so the main example of such tensor products, if you take, okay, so A to B, so D of R1, where R1 So is a K algebra, and same B is D of R2. Same. So the tensor product, A tensor B, is the category of modules over the tensor product. And kind of this tensor product is built in so that these things are true. Okay. All good so far? Okay. All right, and so to make sense of traces, so I also kind of need to tell you what is a collection of generalizable objects, and in general this is difficult. So it's difficult to describe. Or at least I don't know a general description of this. So I will rather give you a large collection of objects, of categories, which are generalizable. Okay? So, so here's a lemma. So if you take C in P1, which is compactly generated, then C is generalizable. All right. So you can describe the dual as well. So if you write C to be ind of some category of its category of compact object, then you can describe C dual as the incompletion of the opposite category of this compact object. And so I can tell you what the evaluation morphism is. Sorry. So I should say that I have not told you what the monoidal unit is. Okay, so let me do it on the side here. So the monoidal unit in P1 is D of K, or vect K. So the category of K, the derived category of K vector spaces, and that's because I've only selected K linear categories. If you want, you can take a more absolute thing where you do this over the sphere spectrum, or even just over animas if you want to remove stability. But I really want to stay in the easier setup where things are K linear. Okay, so the unit, the evaluation has to be a functor from C tensor C dual down to K vector spaces, and it's given as the incompletion of the functor from C0 times C0 up, goes from to dk, which sends A, comma B to the mapping space from B to A. Okay, which you view as a complex of vector spaces. Okay.
Can you scroll a little?
Up, like this?
Yeah. If you scroll so fast, you cannot.
Oh, sorry. Okay. All right. Yeah. Yeah.
So is beyond realizable a subcategory of beyond? Like none of this is additional.
Being generalizable is a property. Yeah.
Is it possible to write down the co-evaluation?
So I don't remember. I'm not going to give it to you explicitly like this. And at the end, so I will give you an example using L-adic sheaves. Okay. So hopefully I'll get to the end of this lecture. I'll give you the example where C is the category of L-adic sheaves, and there will be a non-trivial lemma. I mean, it's not a hard calculation, but there will be content in saying what the unit is, so what the co-evaluation is. Okay. Yes.
Is it true that the incompletion of C0 times C0 up is a tensor product?
Yes. So okay. Let me also maybe repeat the question. So so the question was like, is it clear that the incompletion of this is this tensor product? And the answer is yes. All right, so let's do a first example of a calculation of these categorical traces. So we'll take C to be D of R for R some K algebra. Okay. So as a category, this is always the incompletion of the category of perfect R modules. So it is certainly compactly generated, and in particular generalizable. And so here we even have so an isomorphism from the opposite category of perfect R modules to perfect modules over, so what I write as R rev. So it's traditionally written as R op, but so R rev is R as a K vector spaces, but it's the opposite algebra. So it's times Y rev is Y times X. Okay, and I'm doing this purposefully for tomorrow because tomorrow I'm not going to take a ring, but I'm going to take a monoidal category. And then if I start using op to talk about the opposite rings, like I will have too many notions of ops. So I want to kind of preemptively distinguish them. Okay? And this is the same as the category of perfect complexes of right R modules. Okay. All right, and so that
Sorry, that arrow is equivalence, right?
oh yeah, thank you. Yeah. And that arrow is just naive duality, so it sends M to hom from M to R. All right, so it goes to D of K. Okay, and so by the thing we said before, so this is a tensor product of two categories of R modules. So it's D of R tensor R rev. Here's the thing. And so this functor here, this slanted arrow functor, is given by a bimodule, which is just the bimodule R itself. R viewed as an R tensor R rev, comma K bimodule. Okay, so that's for the evaluation. And for the co-evaluation, so it goes from D of K, and it's just going to be given by the same thing. Okay, so again, this is D of R tensor R rev. And so it's given by R, again, viewed as a bimodule. Yes. Okay, let me scroll down a bit. So what so I'll kind of use the following convention. So if I have a functor from D of R1, to D of R2, and if I have M some R2, R1 bimodule, kind of the functor induced by M is the functor that sends some object N to M tensor, yes, that's correct, of R1 with N.
So the slanted arrow takes something in D of R tensor R rev and takes its tensor product over R tensor R rev.
Correct, correct. Yeah, so something R is an R tensor R rev, K bimodule, which is roughly the same as just an R tensor R rev module, which is the same as an R bimodule. okay, with the obvious structure. And then, so I'm saying define the functor from D of R tensor R rev to D of K. And that's exactly using this formalism here.
I think there's something reversed.
Did I reverse something?
First off, your evaluation and co-evaluation, one of them should be the RF.
I think you're right. So you're right, so I might want to put an R ref here. So to view R rev, okay. So yeah, left and right are difficult. So, but I'm not doing anything crazy here. So kind of just, yeah. But yeah, okay. Any other questions? Okay. Okay. So let's now compute. So now that I've given you the evaluation and co-evaluation, let's compute the trace of the identity on D of R. Okay, so now we just need to unravel the definition and of the evaluation and co-evaluation. So if you remember, so you start from D of K, we go to D of R, tensor D of R rev. Okay, and then, so if you remember, so then we have to compose with the functor which we're taking tensor identity. Here's the functor, it's just the identity, so I'm going to skip this step, and then we just evaluate. So it's co-evaluation and evaluation here. And then, so in terms of bimodule, so it's given by R as a bimodule, and here by R rev as a bimodule. And so it's so the composition here is given by a bimodule from over K and K, so that's just the datum of a vector space, and it's given by the vector space R tensor R rev over R tensor R rev. Okay, but that's a non-trivial operation, and so this thing is usually what people will call a Hochschild homology. What?
That thing where it's R tensor R rev and then the same thing below it. You maybe put a parenthesis.
Like something like that?
You can make it smaller. I'm just saying like.
I'm not sure what you want me to do. So wait. Do you want me to just rewrite this bigger?
Something like that.
Okay. So like R tensor R over R tensor R rev, something.
One more rev.
Okay. Yeah. Okay. All right. And then so now if I take the slightly more general example of if I take a genuine endomorphism, so from D of R to D of R itself, so that endomorphism will be given by tensoring over R with some kind of bimodule M, so M some R bimodule. Okay, so we can just perform the same computation. So the trace of, I'm simply going to write M on D of R. So again, it's a map that goes from D of K to D of K. And so it's going to be given by tensoring by a single complex of vector spaces. And so maybe let me write the answer before doing the calculation. And it's going to be the Hochschild homology of R valued in the bimodule M. And let's check this. So you start from D of K, you go to D of R, tensor D of R rev. M tensor identity this time, and I can't skip this step. D of R tensor D of R rev, D of K. Here I have an R rev, I think. R. Okay, and the composition now is, okay, so bear with me for a second. So it's R, I think I have to start the other way. So the first R goes to the right over R tensor R rev. Then M tensor R, sorry, not identity. So with R tensor R rev, okay, and you just unfold the definition. And that's it, okay. And then you can simplify some of those guys. So specifically, this thing here is going to simplify this R rev and this R, and you're going to be left with M tensor R over R tensor R rev. I'm sorry, it's still not big enough for you, but okay. I visibly have an R rev that is switched from the calculation before. Okay, and like, if we start to look for like sign mistakes like this, we can just spend the day on this. So kind of like, it's something that we can figure out not during a talk. Okay? Okay, and so one of the upshots is that this notion of traces is just a formal way to encapsulate the whole theory of Hochschild homology. Okay. Oops. So now I want to do, depending on how much time I have, that's fine. Okay, so now I want to do a small interlude. So because if you've ever seen the theory of Hochschild homology, you've certainly talked about bar complexes. So let me just say something brief about this. Right, and so the whole point of the theory of bar complexes is to give you resolutions of R as an R bimodule. And so specifically, you have a simplicial object, an augmented simplicial object that goes like this. Okay, and this first map is just multiplication. And these two maps here, since X tensor Y tensor Z, to XY tensor Z and X tensor YZ, and so on. So that is my simplicial object. That is the augmentation. And in terms of complexes, this gives you a resolution of R as an R bimodule. So yes. So tensors, so implicitly all these tensors here are over K. Thank you for the question. Yeah. Yes?
Drop the ref, but it should be there, or you shouldn't be there?
Where?
Should be a ref there or not?
On this top line here, like?
No, in the interlude.
In the interlude, there's no rev. Okay? So they're all over K, but I mean, I'm saying K is a field to kind of like make our life easy. K can be arbitrary. Okay, and tomorrow I will use the fact that kind of these bar complexes, I mean, they work in a rather large degree of generality, and so they also work for categories. Okay. I mean, okay, so the only thing I'm saying is that you have a simplicial object like this, okay, and it gives you, like when you pass to complexes, it gives you a resolution of R as R bimodules, or as R tensor R rev modules. Okay. All right, and then so in general, so I mean the usual theory of Hochschild homology basically tells you that for a bimodule M, HH of, sorry, not A, M is given by the geometricalization of like a certain simplicial object, which is R tensor M. And these are two maps, oops, sorry, that sends X tensor M to XM, and the other one sends MX, and here it's, so I should put one more time. And so X tensor Y tensor M, it will go to XY tensor M, X tensor Y M, and Y tensor MX here, and so on. And this is the same as, so maybe, sorry, maybe let me give a name to this thing. So bar complex of R, and it's the same as B of R tensor over R tensor R rev with M. And it just recovers some very classical constructions, right? So, but the point is that kind of this notion of traces is just defined abstractly, and it just recovers like this usual theory of Hochschild homology and bar complexes and so on. They're all kind of included in the machinery. Okay, and the point of this interlude was also kind of to give you kind of a general way to compute these things, at least for our modules. Okay. Okay, so now some general functorial properties.
The active value symbol, like for the realization.
Yeah, it's geometricalization.
But these are complexes, so you just take the alternating sum.
Yes. Yeah, yeah. Okay. So I think I want to list 4 properties, which are, and 3 of them are properties you already know. So the first property is that it's compatible with transposition. So if you have, so we'll take C to be a dualizable category, and F some endomorphism of C. So since C is dualizable, you have a good notion, you have a C dual, and you also have an F dual attached to this, just like you would for vector spaces. And so, oh, thank you. Yeah. And so as you know, in terms of matrices, like for vector spaces, this would just be corresponding to passing to the transpose of the matrix, and the trace for a matrix and its transpose are the same, and it's a very general categorical property. So there is a canonical isomorphism between the trace of F on C and the trace of F dual on C dual. Okay, so that one shouldn't surprise you. The next one should not surprise you either, so it's some cyclicity property of the trace. So we'll take C to D back to C, F and G, with C and D dualizable. Just not too much. So I have until noon, right? I have until noon. Yeah, okay, thank you. Okay, so for C, F and G morphisms like this, so you can take the trace of G composed with F on C, and, well, okay, same property you know for vector spaces is true here, so it's isomorphic to the trace of F composed with G acting on D this time. Okay. Let me say kind of these first two things, they're kind of diagram exercises. And I actually didn't prepare them, but they're not super hard. Okay, so it's a good exercise to try to do them. Okay. The third one is the monoidality. So if you take C and D two categories with some endomorphisms like this, so with C and D dualizable, then C tensor D is again dualizable. And so the trace of F tensor G on C tensor D is just the tensor product of the two traces. Okay, so far all these properties shouldn't surprise you, because these are things you know for the usual notion of traces. The last one is the actual functoriality of traces. And it comes from this fact that, okay, before we were taking traces on vector spaces and we got out scalars, and there are no maps between scalars. But if you go up one categorical level, there are non-trivial maps between vector spaces. So the fourth one is the functoriality. So we'll take C and D, again, so dualizable. Okay, and we'll take a morphism phi from C to D, so which admits a right adjoint. So let me comment on this. So phi is a morphism in PR. So it's a morphism, it's a functor between categories. And so this, in PR, all functors have a right adjoint. And that's one of the main reasons to use presentable categories. Now, what I mean by admits a right adjoint, I mean admits a right adjoint within the category of presentable categories. Exactly. So, which means the following. So, phi R exists as a functor, but I want this phi R to be also in PR. So, but we ask in PR, meaning that phi R commutes with colimits. It doesn't need to commute with colimits for this thing. So it's vect K is a rigid category, and so whenever you pass to the adjoint, you have a lax linear. You automatically lax linear over whatever you are linear over, and the rigidity forces lax linearity to be linear. So phi R is already K linear on the nose without this property. Yep. Okay. Okay, and then we want a diagram like this. So we want C to D. So C to D. So here we have F, G, phi, and then we want a natural transformation between them. So, which goes like this. So alpha is a natural transformation between phi F to G phi. Okay. And now, so once I have all this data, I can define a map. So trace of phi comma alpha, which is a map from trace of f on C to trace of G on D. Okay, and it's the following composition. So you start with trace of f on C. You use the unit of phi to go to trace of phi r f on C, and this is where we need phi r to also be a morphism in PR, because we want to take the trace. We can only take the trace of a morphism that's inside of the category. And so if phi r was not in the category, like this first trace here wouldn't make sense. Then we use this cyclicity property, which is this property number 2, that's kind of right above here. So we're going to permute these functors. So I think I want trace of phi r f Sorry, I messed up something. So it goes to the right adjoint. D this time. Scroll down a bit. Then I can plug in alpha, which is a natural transformation from phi f, the first two terms here, to g phi r, d. And then you can use the co-unit of phi. So that's a general construction, and it is, in general, rather difficult to compute. It is a very powerful construction, but kind of making it explicit is usually like kind of the interesting thing to do. Okay? All right. So, and one of the very important examples of this functoriality is the notion of Chern characters. So we'll take the following setup. We'll take C to be dualizable. F, an endomorphism of C. And we'll look at the following kinds of functorialities. So we'll look at the functoriality from D of K with the identity. So as a category with an endomorphism, to see the category with F. And so that arrow here is the data of the pair phi alpha that I had before. So, all right? And so let's just unravel what this data means. So phi is a functor from D of K to C. And so since we're in the category of K-linear categories, this is just the data of an object small c in C. And this functor sends K, the one-dimensional vector space, to C phi. Okay? And phi r being continuous is equivalent to C phi being compact. So phi has to basically give us the data of a compact object. And then the map alpha, so if we unravel what this above diagram here gives us, is the data of a map from C phi to f of C phi. And once we have this, we can form, so we obtain a map from trace of the identity on dk, trace phi alpha to trace cf. So the trace of identity on dk is just k itself as just a one-dimensional vector space. And this map points out to, so it sends 1 to an element which I'm going to call class of C phi alpha in this H0 of trace CF. Okay, and now let me give you a very concrete example of this thing, because if it's the first time you're looking at this, you might be like, why are we, like, what is this kind of thing? And it is a way to encode like the notion of a character of a representation. So example of this construction. So we'll take C to be the category of representations, or the derived category of representations, of a finite group gamma. And we'll assume K has characteristic 0. Okay. So in particular, this category is semi-simple, and everything about it is very easy. So, and we'll take F here to be the identity. So, we can also rewrite this as the category of K bracket gamma modules. So I've already told you how to compute this. It's the Hochschild homology of this thing. And so, and the semi-simplicity basically will tell you that there is only a unique Hochschild homology group that is non-trivial, and it's the 0th one. And so what is this thing here? So it's a complex of vector spaces which is actually concentrated in degree 0, and turns out to be isomorphic to the center of K bracket gamma. So it's just a space of characters of representations of gamma. Okay, so that's for the trace, and now for the example of such a Chan character. So if we take M, a representation of gamma, which we'll assume to be finite dimensional. So this finite dimensional property will tell us that, will imply that M is compact. Okay, and so that gives us the C phi of the construction above, and the endomorphism will take, so the alpha from M to, so the functor small f, which is the identity, which applied to M is just M again, and we'll take the identity as well. Okay, okay, and so it's calculation, maybe, that, so the class of M and alpha, for this alpha to be the identity, in this center here is the usual character of M. So viewed as a function on gamma. So, okay? Okay. All right, so I have like slightly less than 10 minutes, so I don't know if it's going to be enough to go through the last example, but I'm going to try a bit. So let's kind of give another example of kind of this notion of traces and kind of what can happen. And the other example I kind of want to build up to is the function shift dictionary. So the setup is as follows. So you take x naught to be we'll take a finite type scheme over fq. X will be base change to fq bar. So it carries an endomorphism, f, which will be the geometric Frobenius. And then our category C is going to be sheaves on x, valued in QL bar. Okay. And I will view this as a category with an action of f lower star. And maybe I should say that this presentation of the dictionary is due to Gatsbury and Warshawski. At least if I get to the construction. Okay. So let's just recall the classical function shift dictionary. So if you take f to be a constructible sheaf, with a Weil structure. So Weil structure here will be a map. Will be a map from f to f lower star of f. So it should really remind you of this class construction. And that's the whole point. So let's call it alpha to be consistent. And then so the construction attaches to a function. So trace of alpha on f. So the classical construction of the Grothendieck function shift dictionary is to define a function out of this from the set of fq points on x0 to ql, which sends to a small point x. So I can view x as an fq point, and so I can, or rather as an fq bar point, and I can pull back the map alpha to this thing. So I can do. And then since x is stable under the Frobenius, this is the same as x upper star of f. And so you send small x as a trace of alpha x on the stalk at x. All right. Okay, and so the game now is to try to reconstruct this map in terms of categorical traces. So naively, what you would want to do is to say, okay, so ideally, trace of f lower star on sheaves x QL bar is just the space of functions on x of fq valued in QL. X0, thank you. So I don't know if it's true, and I think it's very, very false. And that boils down to categorical QNet formulas being wrong. So let me first kind of give you the duality datum for sheaves x. So I'll write sheaves x QL bar as sheaves x from now on. So it's ind of the constructible sheaves. So it's, again, compactly generated and dualizable. And you have Verdier duality, which gives you a self-duality on this thing. And so it induces an isomorphism from sheaves X dual to itself. Okay? So here's a lemma, and I think kind of that's the answer to the question that Jared asked me before. So I have to tell you, okay, what are the unit and co-unit for these things? And so the evaluation map here sends A comma B, tensor B rather, to the cohomology on X of delta upper shriek of A box B. And so this box tensor, here, I view it as a functor from sheaves X, tensor sheaves X, to sheaves on X times X. And that thing is usually very much not an equivalence. But it carries a right adjoint. And so the content of the lemma is to tell you that the unit so that's the evaluation of the duality datum. And the co-evaluation is so the functor that goes from DQL to sheaves X tensor sheaves X, so it's just given by a single object, and it's the object that the image of QL is, so box R of delta lower star of the dualizing sheaf. And so to prove the lemma, the proof of the lemma is a direct calculation. So now that I've given you the two functors, you just need to unravel the composition to check that the composition is the identity. Okay? And so now the construction so am I okay, I just need 1 more minute of Gatsguri-Warshawski is the following. So you have this trace, which is this composition. So that's going to be the co-evaluation and the evaluation. And it's going to be F lower star tensor identity. And going the other path, so this we can always embed in sheaves X times X. Okay, and so I will write functors here, which is cohomology of delta upper shriek. Here I'm going to do F times identity lower star. And here I'm going to do, so a functor out of DQL is just given by an object, and this object is delta lower star of X. So I'm writing this diagram to construct a functor out of the categorical trace, which is the composition of the first row. And so these two squares, they commute on the nose. Essentially, so by definition of the evaluation map, and the middle one just visibly. The one that's not obviously commutative is the left one. And so here there is a non-trivial 2 map between the composition. And so this 2 map goes from box of coev, which is box R, delta over star omega X. And box R may not be isomorphic to the identity, and that's reflected by the fact that this categorical QNet formula is not true, so that the embedding is not essentially surjective. But you still have a map to delta star omega x. And so if you track down what is the composition downstairs here, so that's given by taking the cohomology of the Frobenius fixed points valued in the dualizing of this, and it's just the space of functions on this finite set. And so that diagram defines a map from, from the trace of f lower star on sheaves x to fun on x f ql bar. And given, and so the theorem is that given a sheaf f with a veil structure, so the class of this thing, so in H0 of the trace, is sent to the usual function. Is the function of the Grothendieck function sheaf dictionary. Oops, sorry. Okay, and I will stop here.